Hey everyone. So we begin our second half of Trig in that we're doing trig equations and identities. And to begin with, we're going to look at first degree trig equations, solving them algebraically. Now, we actually have already done this when we were looking at working backwards on the unit circle. It's just now we're going to make them a little more complicated, but still solve them. So basically, solving a trig equation is similar to solving a polynomial equation, the equations that you've mostly done so far, like quadratic and linear equations. Except one initially treats the trig ratio sort of like the variable in that you need to isolate it if it's a first degree equation. Or if it's a second degree equation, you're going to factor it. And we'll do that in the next lesson. If the angle or the argument is a double angle, then replacement with an identity will be necessary first, okay? And that's going to be covered after we talk about identities. So let's look at the first situation. So we're going to look at a first degree equation, so that means the exponent on our trig function is just a 1. Exact value for trig ratios, in other words, it's on the unit circle. Okay, so here's our steps. We want to isolate the trig ratio, and next step, if you have a cosecant or a secant trig ratio, you want to flip or reciprocal both sides of the equation to get the primary trig ratio of sine if it was cosecant or cosine if it was secant. Then determine the angles, so then you'll have something like, sine theta equals 1/2. So then you're off to the unit circle to determine the angles and write the answer, theta equals or beta or whatever it is, as a specific solution or solutions given the specified domain. Okay, so that usually goes along with the question. If the domain is not given or it's specified as all real numbers, then you write something called the general solution. Okay, so we're going to define that here, and we're going to practice that a little bit too on this first set of examples. General solution really is a way, and we touched on this a bit when we were doing tan graphs and we were describing the asymptotes. It's a way to describe all answers, essentially, for all real numbers. So typically, though, for first degree equations with trig ratios of sine, cos, cosecant, or secant, the general solution is really you take the angle that you would have written down if it was specific solution, and you go plus 2 pi n, where n is an element of the integers. In other words, you're adding full rotations to the first angle. Or if you're working degrees, again, the angle plus 360 degrees n, where n is an element of the integers. Okay, so that being said, you still want to look at your unit circle once you've got all the terminal arms that are solutions drawn, and then determine how you would describe it generically. The other thing, so that's typically for sine, cos, cosecant, and secant. If you have a first degree equation with tan or cotan, you typically take what would have been your answer plus pi n if it's in radians, or in degrees, the angle plus 180 degrees n, okay? Where n is an element of the integers. That's because with tan or cotan, the other answer is always in a straight line from the first answer. So it's really just 180 apart. And you could connect that to graphs as well, where the period for tan and cotan is pi or 180, and for sine, cosine, and the other ones, it's 2 pi or 360. Okay, let's take a look at these questions. So, determine the angles for each of the following trig ratios and domain, so given the domain here. And that's going to switch up every time, so you have to kind of make sure you're looking at these domains, okay? So let's look at the first question. All right, go through there. So beta is our angle, okay, and we've got a cotan on this side and a cotan on that side. Well, we need to get those on the same side. So what we're going to do, first of all, is expand. There's two terms inside the brackets here. We're going to multiply that 2 through, so that, oh, super messy writing, so sorry. Okay, I'll try and clean that up a little bit. There we go. Okay, now we have this cotan term and this cotan term. We want to focus on getting that on one side and preferably have it positive. So I think we're going to subtract 4 cotan beta to the other side. So 5 cotan beta minus 4 cotan beta would be just 1 cotan beta. Okay, and at the same time, let's add the 1 to the other side. So plus 1, and we would have negative 1. Negative 2 plus 1 on the other side, so negative 1. And there we go. Now we essentially have cotan beta equals -1. Now these now are like the questions we did when we were working backwards from the unit circle. So let's see if we recognize this on the unit circle. Cotan, what pops into our head when we hear cotan? X over y. So how would we, for a point on the unit circle, get cotan, the combination of the x and the y coordinate over top of each other, to equal 1 or -1, let's say? So essentially we would need to be at the root 2 over 2, root 2 over 2, or the quarter pies. So we would have to be, and if it's going to be negative, one of these, either x or y, is negative. So it would have to be here. And the other answer for tan and cotan, always in a straight line. So down there. Okay, so we have the terminal arms now. Take a look at your domain, and we want to name those terminal arms within that domain. So we would write beta, whatever the angle is inside, equals. Okay, from 0 to 180 then, we're in degrees, and 0 to 180 would be from there to there. Well, we really only hit this first terminal arm, don't we, in quadrant 2. So that would be an angle of, that's the 45-degree reference angle, or an angle of 135. This one down here is not in our domain, so we can't really use it, and our only answer would be beta equals 135 degrees. All right, let's take a look at example number 2 here. 3 secant alpha, so another Greek alphabet letter, minus 6 equals 0. So again, we want to isolate, kind of see this as the thing we need to isolate. We want to isolate secant alpha. So we are going to add 6, first of all, to the other side. You always want to eliminate your adding, subtracting first. You basically are reversing bed mass is what you're doing. So we're getting rid of adding, subtracting, then getting rid of multiplying and dividing, and then exponents, etc. Okay, so now divide by 3, and we'd be down to secant alpha equals 2. Okay, now this is now step 2 that I was talking about. If we have a secant function, we now want to reciprocal that and change it to cos. So I just flipped the left-hand side, so I'm going to flip or reciprocal the right-hand side. And there we go, off to the unit circle. Whereas cos positive, so cos is x, right? Whereas x positive, that'd be quadrant 1 and 4, and 1/2 is your little coordinate, so it would have to be here and here. See how the unit circle is coming back to either haunt you or help you, depending on how it went, last half of the unit. Okay, so we want to name those angles between -2 pi, okay, which means we're going this direction, okay? And so let's name this one here in quadrant 1 first by going all the way around in the negative direction. Those are thirds of a pi. All the way around would be -6/3, so 1 less. So we'd have alpha equals -5/3 of a pi. And then this one would just be 1/3, so -1/3 of a pi. And there we go, between -2 pi and 0. Awesome. Okay, now that's sort of a review from what we've done already. Number 3, you'll notice we have 1 plus sine x equals 0, where x is an element of the reals. So they're really saying we have to name all of the terminal arms, okay, for if we go many, many times around. So let's back up. We're going to isolate our trig function again. So sine x equals, subtract 1 to the other side. All right, and we're there. It's not a reciprocal function. So off to the unit circle. We want to know where sine, which is y, is -1. Now that's a special number, right? That happens when you're on the axes here. So coordinates there would have been 0, -1, and sine was -1 down there. Okay, now we could name this terminal arm really as anything. I probably should have specified that we'll make this one in radians, and this one we'll do in degrees over here. Sorry about that. Okay, so so if this is in radians, we want to go with our principal angle, which would be the smallest positive angle to get to that terminal arm. So x would equal, and that would be 3/2 of a pi. 1, 2, 3/2 of a pi. Okay, now we want to be able to get back to this terminal arm by adding a consistent amount, which really would be a full rotation, right? So if we add 2 pi, we would hit that terminal arm again, or subtract 2 pi, same idea. We basically want to add multiples of 2 pi. So where n is now many integers, meaning we're adding or subtracting whole amounts of 2 pi. And there we go. That would be a general solution. So general solution for that particular equation. So in other words, all of the answers. Okay, let's try number 4. So we have 3 tan y. Okay, so now our angle is being called y. We still want to isolate our tan function, our trig function. So we go tan y equals, we're dividing by 3 to get that to the other side. Okay, so root 3 over 3. You might not recognize this, but what this is, it's kind of the rationalized version of 1 over root 3. And how do you know that? Let's kind of unrationalize it by multiplying the top and bottom by root 3. Sort of like we're rationalizing the numerator. And that would become tan y equals, on top we'll have 3, which is root 3 times root 3. On the bottom, 3 root 3. There we go, the 3's reduced, and we're left with 1 over root 3. Ta-da! Okay, now why did we want to do that? Well, we wanted to recognize that tan is y over x. Normally root 3 is root 3 over 2, and if we're going to divide the bottom by 2, we better do that to the top as well. Okay, so now you see it, right? X is root 3 over 2, y is 1/2. Okay, they're both positive, so let's try quadrant 1 here first. So y is little, that's the 1/2. X is big, so we would be here. The other answer, straight line because it's tan. Okay, and now we want to name these terminal arms for all real numbers in degrees. So y equals, this first terminal arm would be 30 degrees. Okay, now it's a little weird with tan and cotan, but we don't actually have to name this second terminal arm, and I'll show you why. If we add, or in degrees, so 180 degrees to this terminal arm, we will arrive at the other terminal arm. If we add another 180 degrees, we would then arrive back at the original one. So all we have to do to name both of these terminal arms is start with 30 and add multiples of 180 degrees. So 180 degrees times n, where n is an element of the integers. And there you go. That would cover all of the answers, or the general solution. Okay, cool. Let's take a look at the next page. Okay, so we have a second part to this lesson, and we will actually literally have a part 2, I believe, with another video. It should be a short one, but what we're going to look at now is first degree equations again, so exponent of 1 on our trig function, but now decimal value for the trig ratios. In other words, we're going to have to use a calculator, okay, instead of the unit circle. So first 2 steps are the same. You want to isolate the trig ratio. If it's cosecant or secant, you're going to reciprocal both sides to get the primary trig ratios. Then, this is where it differs. So how do you know you've got one of these? Well, you look at the coordinates and you go, those do not look familiar. So we're probably not using the unit circle. We're going to be using the calculator. So to find the angles using the calculator, basically start with trying to find the reference angle by going the inverse trig ratio. So if it's like tan, you'd go inverse tan or second function tan on the calculator of the positive or absolute value of the trig ratio. I'll show you what I mean on the first example here in a second. Determine which quadrants that trig ratio would be positive if that's what we're doing, or negative, right? Draw those terminal arms in the correct quadrants with the proper reference angle. Then using that reference angle, determine what the rotation angles would be given the domain. And again, if the domain is not given or it's specified as all real numbers, you write it as a general solution. Okay, so let's put this to work on these examples. And you know what? Maybe we'll start a new video to do these examples, and we should be able to finish them up within a few minutes. And we're going to need our calculators, so if you don't have yours, please get it now. And I'll see you in part 2 of this first video, or this first lesson of Trig 2. All right.